Section 3.1, Function Notation. Function notation is just about rewriting our equations in a different way. For example, let's take a look back at the Patriots logo you see here, logo of the New England Patriots. This was the symbol that was in their end zone for the last several years, a decade or so. And recently, just a couple of years ago, they updated and they have this new and improved logo here. And we can see their new and improved logo. Maybe you can debate whether you think it's improved or not, but this is their new logo that shows up in the end zone. There's no difference. It's still the same Patriots team. Bill Belichick's still the coach. Tom Brady's still the quarterback. They still play at Gillette Stadium. But it's just a new look. It's a different look to the logo. And that's all that function notation is. It's a new and improved look. And really what changes is we go from, we used to use y, and we're going to replace it with this symbol here, f, and then in parentheses, x. And the way we read that is we say y equals f of x. One important thing to keep in mind here is that even though there are parentheses, this is not multiplication. It means something else, which we'll see in the next couple of pages, but we're not multiplying f by x. F of x is a thing together. And so just to show you a specific example of this new and improved look, our old version was y equals mx plus b, what you'll remember of from the last section as slope-intercept form. Well, we're just going to rewrite it now and replace the y with f of x, and so it's going to say f of x equals mx plus b. It's out with the old and in with the new, just like with the Patriots logo. Old logo, new logo. It's the same thing, it just looks different. All right, let's see how we can use this now. One thing we can do is we can evaluate a function. And in the last page I used f of x. It doesn't have to be f. F is the most common because f stands for function. But I've given you two examples here. One is f of x, the other is g of x. It really could be anything. And so I'm giving you these two functions. F of x equals 2x plus 7, and g of x equals 3x squared minus 2x plus 3. We're going to evaluate both functions at these three values for x, 0, 2, and negative 1. The key word here is evaluate. That means we're going to be getting a number for an answer. And that's convenient for when we go through this. Now, to do the first problem, I'm going to do f of 0. To substitute in here, or to evaluate, all that I'm doing is a substitution. I'm saying f of 0 equals 2 times 0 plus 7. And now I just go ahead and do that work out. 2 times 0 is 0, plus 7, and 0 plus 7 is 7. So my final answer would look like this. F of 0 equals 7. Now again, all that I did there is I took my original function and I replaced both x's with the x value that I'm given. X equals 0. I'll do the same thing for g of 0 on the other side. I'm going to take g of 0 and I'm going to rewrite this function using zeros instead of x's. So I have 3 times 0 squared minus 2 times 0 plus 3. Well, 0 squared is 0. 2 times 0 is 0 plus 3. 3 times 0 is 0. And then going across here, 0 minus 0 is 0, plus 3 is 3. So we have g of 0 equals 3. We're not going to divide each side by f or g or 0. That's what our final answers look like. All right? Let's try it again with 2 for each of them. Again, I'm going to plug in. I want to know now what's f of 2. That's 2 times 2 plus 7. 4 plus 7, and 11. So f of 2 is 11. And that's just, again, plugging in, replacing every x with the number that I have there. Let's do the same thing with g. G of 2 equals 3 times 2 squared minus 2 times 2 plus 3. 2 squared is 4. Negative 2 times 2 is minus 4 plus 3. 12 minus 4 plus 3. That's from 3 times 4. And 12 minus 4 is 8. And 8 plus 3 is 11. Oh, that's pretty interesting. The g of 2 and f of 2 are both the same thing. That is just a coincidence. That won't happen all the time. But that's what you have to do. All right, let's scroll up a little bit here, give ourselves some room. I want you to go ahead and pause the video and try to evaluate f of x and g of x both at -1, then come back and see how you did. All right, how did it go? And so there you go. F of -1 is 5, and g of -1 is 8. One thing to keep in mind here is that you have to do the exponent first before you multiply by 3, and therefore, and also remember that -1 squared is a positive 1. So that might have been something that could have led to some trouble, but otherwise should have been all right. And so that's how you do it. That's how you evaluate a function. All of our answers there are numbers, and these correspond to ordered pairs, actually. And we'll look at that on the a later example. All right, let's take a look at something else. All right, so sometimes we're not going to be told what x is, but maybe what the function value is. So in this example, I'm telling you to find the value of x, which is the independent variable, so that h of x is 7. H of x is just another function, and I'm telling you that h of x equals 9x minus 11. Now, because h of x as a whole group equals 7, I'm going to replace h of x as a whole group with 7. Again, this is not the same as plugging in 7 for x. I'm going to take h of x and say instead of that whole thing, I'm just going to use 7. And that's going to equal 9x minus 11. Now I just go and solve for x. Add 11 to each side. That's going to give me 18 equals 9x. Dividing by 9. And I get x equals 2. That's my final answer. If I wanted to do a check, I really want to show that h of 2 equals 7. That's what I'd want to check. And I check that by plugging 2 in to my function for my x. So it's 9 times 2 minus 11, 18 minus 11, and 7. That's perfect. That's exactly what I wanted. And so my answer would be x equals 2, and that's how I'd solve for my independent variable. Using the same function, I want you to now pause the video and try to do it for h of x equals -2, or h of x is -5. Do it for both, and then come back and see how you did. All right, let's take a look. And so there you see, we just replace the h of x with -2 or with -5 and solve each problem. And I've just changed the order so that it's the x is on the left, but in the first case, x equals 1, which basically means that h of 1 equals -2. And that's what this basically means here. And the second one, I just reduced the fraction. 6/9 is the same thing as 2/3. So even though we get a fraction, there's nothing wrong with that. And this is basically saying that h of 2/3 equals -5. So that's the comparison that we have there. All right, hope this makes sense. Seems like it's pretty straightforward so far, and it doesn't get much harder than this. Now, if we want to graph a function, we're going to use an input-output table. That'll give us points on the graph. Now, unless we're told what the domain is, we can pick any values that we want to use for the input. And so in order to do this input, I'm just going to pick kind of some easy values. It's always good to start with 0, and then maybe we'll just pick some other ones. 1, 2, 3, and 4. We'll have a bunch of examples like that there. And to figure out the output, all I'm going to do is I'm going to plug these into my function. So the first one that I'm going to do is f of 0. I'm trying to graph this function here, f of x equals 3x minus 6. So f of 0 is 3 times 0 minus 6. 3 times 0 is 0, and minus 6 is negative 6. And so what I have there is I have an input of 0 and an output of negative 6. That's an ordered pair. 0, negative 6 is really what I'm looking at there. I could repeat this for f of 1. f of 1 equals 3 times 1 minus 6, which is going to be 3 minus 6, which is negative 3. So 1, negative 3 is going to be another ordered pair. Go ahead and pause the video and complete it for the other 3 inputs and find the 3 outputs that you need. All right, how did that go? All right, so there you go. And maybe at this point you actually have spotted the pattern where to get from 1 to the next, we're going up by 3. And since I'm going up by 3 with my outputs as I go up by 1 with my input, that constant rate of change confirms that this is indeed a linear function, which is what I expected. Now I would want to take each of those 5 ordered pairs, 0, negative 6, 1, negative 3, 2, 0, 3, 3, and 4, 6, and graph them. And so using a graphing calculator, I've done just that. I can zoom in here and look at the graph. And you can see that when I plot these 6 points, or 5 points I should say, they do line up. And I have a graph here. I can connect them and go on forever to show that I have a line. And that's how you do it. If the points didn't line up in a line, you might have some type of a curve, like a parabola or something that would follow this dot like this. But otherwise, if it's a linear function, you'll just be able to connect them and form a line. All right, let's see this used in real-world examples now. All right, so let's talk about how we can model a real-world problem with a function. If we use the function h of x equals 300 minus 25x, we can represent the height of an airplane above the ground during the end of its descent, where h of x is the plane's altitude in meters and x is the number of minutes that have passed. So we can graph the function using an input-output table and a scale. We're talking about big numbers here, so we're not going to just use a scale of 1 to 1. We'll mark our graph accordingly. Then we're able to interpret different parts of the graph in the context of the problem. So let's start with generating this input-output table. I always do think it's a good idea to start with 0, but I'd kind of like to get a big jump here because I am thinking 300 is such a big number. It's going to be tough if I graph these too close together. So you could pick whatever numbers you want. I'd recommend 0, 4, 8, and 12. And so again, just as a refresher, in order to fill in this input-output table, we're going to do h of 0, which is 300 minus 25 times 0. 25 times 0 is 0, obviously, and that's just going to be 300. So 0 is 300. So go ahead, take a minute, and fill in the rest of the outputs, and then come back and check, and I'll show you what you should have. All right. So there you go. Should have been pretty straightforward there. But you get 0, 300, 4, 200, 8, 100, and 12, 0 as your 4 ordered pairs. Now what we're going to do is we're going to graph them on a coordinate grid, and we're going to put a scale on there so that we can actually look at it within a reasonable space. Let's see what that looks like. So you can see here I have my function h of x equals 300 minus 25x. I have my 4 points labeled. I've got my axes labeled, time in minutes, altitude in meters, and I've connected these points. This is a continuous domain because it makes sense to have kind of not just whole minutes, but every second counts, and so the plane is constantly losing altitude as it descends to the ground. Now we can look at different parts of this and try to figure out what might be significant here. So let's look at the point 0300 first. The point 0300 is the y-intercept, and that's really the starting point that we have here. Y-intercept is generally speaking a starting point. After 0 minutes, we are 300 meters in the air. That's where we are at the very beginning. After 0 minutes is at the start. So at the start of this descent that we're looking at with the linear function, we're 300 meters in the air. That's our starting point, our highest point. What about the other intercept? The x-intercept, 12,0, is when we're at an altitude of 0 meters. That's at ground level. And so the x value there, 12, tells us it's going to take us 12 minutes to land. Now, these two intercepts realistically also tell us about the domain, because we know that we are not going to be going into negative time or into negative altitude, and so the domain here is really just from 0 to 12 inclusive, which means that we really shouldn't even have these graphs extended. But that's all right. We can still establish our domain is really from 0 to 12 inclusive, and writing it like that, which would mean that our range would be similar. Our range would also be bounded by this. We're not going to go above 300 meters. We're not going to go below 0 meters. So that's what our range would be. There are other things we can look at too here. We could look at a particular point on the graph. By looking at this point here, which has the coordinates 6, 150, what we could really say is that h of 6 equals 150. That means that when that 150 meters, the plane is 150 meters above the ground after 6 minutes. And so there's a whole lot that we can see here. We could use this graph to figure out, when will it be at 75 meters? Well, 75 meters is the height. And go over to our graph and say that must correspond to about 9 minutes. We could check that and see if that's true, and I think it will be. We can see what's its altitude after 3 minutes. We go up to 3, up to the graph, and go across, and that appears to be 225 meters as our altitude. So these are all the different things that you can do using the graph of a function. I hope this makes some sense and that now you find these useful going forward.